So before we can really start talking about our polynomial functions, we need a good understanding of power functions. So power functions are of this form where you have this a with the subscript of n times x raised to a power of n. Now this number out front, that a with the subscript of n, is a real number. So it can be positive, negative, it could be a decimal. It's just a numerical value out front. So that's our numerical coefficient. Sometimes we just say coefficient for short, but numerical coefficient. And then our value n, which is our exponent, is a non-negative integer. So we won't see any negative exponents there for here, and we won't see any rational exponents like 1/2 or like to make it a radical function. So with that, we'll have non-negative integers. So with that, we're going to see values for n that are more than or equal to 0 and are a whole number. So some examples of power functions, we could have like 2x to the 5th. That would be a power function. We'd have x to the 12th. So that would be a case where that a with a subscript of n would just be equal to 1, and then times x to the 12th. We could have negative 3x squared. We could have 1.5 times x. Basically, a number out front that's a real number. And then for our exponents, well, in this case, we have this exponent of 1 hanging out there, but we have these non-negative integers. Now, the case where we could have a power of 0, and this is kind of weird for a power function, but it will come up with our polynomials. Let's say we just had 5. This is technically 5 times x to the power of 0, which is allowed for a power function. It's just that when you raise anything to a power of 0, that all just turns to 1. So seeing just the number 5 is technically a power function. Not a very interesting one, because that would just be a horizontal line at 5. Even this 1.5x just makes something linear, but they are power functions. Okay, so let's talk about these basic power functions. So x squared, x cubed, x to the 4th, x to the 5th. So x squared we're pretty used to. That's our parabola. So without anything else multiplying on or adding on, which is really what we're trying to avoid here. We're not going to be adding on anything to the end here. It's just about this number times x to the n. So if that number is just 1, we can see our parabola. Now, if you think about plugging in different values for a subscript n, for an, well, like if we did 2x squared, what would that do to our function? Well, that would make the vertical stretch occur. So I would stretch it out like that. And same thing if we did 10x squared, it would stretch it. So this value for the a subscript of n causes a vertical stretch. Something we'll want to make note of, though, is with that numerical value, overall the trend stays the same, and this trend we'll talk about more in the next video. But overall it keeps this kind of same shape somewhat, it's just stretched up. Now what happens if I chose a negative number? What if I just did -1, so negative x squared? Well, then my graph would look like, let's see, what's our scale here, 2's? Then our graph would look like this. So overall same shape, it's just reflected over the x-axis. So that's something we'll need to pay attention to as well. If we see this numerical coefficient, let's see, if an is negative, then reflect over the x-axis. So when we have this an, what we're going to do is focus on this power function part, that x with a certain exponent, but then a with a subscript of n is going to cause this stretch, and we just need to pay attention to if it's negative, because then it will reflect over. Now, x squared is our general parabola shape. Let's jump over to x to the fourth. And what we can see is it flattens out a little bit around 0, but overall, it's a very similar shape. In terms of trend, coming from positive infinity, going to 0, going off to positive infinity again, very similar trend to x squared. And if we kept plugging in even exponents, we would see the same thing occurring. So let's even go over to Desmos. So we saw x squared, and if I do x to the fourth, just kind of flattens a bit, especially it's for those fractions that are between 0 and 1. And then once you hit 1 and then 2, like the exponent makes it grow very, very fast. If I do 6, 8, 10, overall, I mean, we're seeing a difference in shape around 0, and this is something we'll talk about, this kind of idea of short run behavior, this behavior that's occurring in the middle, which we'll talk a lot more about. That changes, but in terms of what's happening up here, and that's what we would call the long run behavior, it's staying the same. Like it's coming from positive infinity and goes off to positive infinity. So this is a behavior of even power functions. And that we can have this general shape of our graph. As long as we know that it's an even power for n, we know that there will be a general shape like this, or depending on if an is negative, or it would flip and open downward. So that downward case is when an is negative. So with that, we can look at just the exponent of our power function, and if it's even, we have this idea of a general shape. Now for x cubed and x to the fifth, we can see the same thing happen. So if we can really remember the general shape of our x cubed function, it holds true for other odd powers as well, even though there's this slight difference in flattening and there are differences in output values, the general shape is the same. So with that, when we have odd power functions, we'll have this general shape, and I always think of it reading left to right. It comes from negative infinity and goes off to positive infinity. So that's our general shape for an odd power function. Now if an is negative, then what we would see is this reflection over the x-axis, which would cause it to do something like this. So let's go with or, coming from positive infinity off to negative infinity, and that happens if an is negative. So these are the general shapes of our power functions. If we focus on just the exponent, we can get an idea of the general shape just based on it being even or odd. And then just in terms of direction, we'll need to pay attention to an in terms of whether it's positive or negative. Positive would go with our most general form that we would expect, and then if it's negative, it would switch direction by reflecting over the x-axis.